everyone, and welcome back. Today we're going to revisit a problem that we talked about a little while ago, but we're actually going to be presenting a better way of solving that problem. In particular, the problem that we're going to be solving is testing the null hypothesis that means mu1, mu2, mu3, all the way out to say mu k, where k is bigger than or equal to 2, are all equal to each other. And the method that we're going to be using here is what we refer to as a one-factor ANOVA, and there's actually two different ways of going about a one-factor ANOVA, and we're going to be going about it in the multiple regression approach. Right? So let's first off talk about how we solved it before and the downsides of it. So remember, before we used what we call a pairwise comparison tests. That is, what we did was we looked at, for example, the null hypothesis that mu I is equal to mu j, where I and j range from 1 to k and of course are not equal to each other. But the downside of that was that we had ck2, or k factorial over 2 factorial times k minus 2 factorial number of tests that we had to conduct in order to sort of, get a reasonable conclusion out of that. But if that's the case, that means we also had that many type 1 and also type 2 errors that could result as a result of that particular testing approach. Okay, which definitely isn't good, right? So if you have a lot of means that you want to test the equality of, then you have several different type 2 errors that could occur. So we, of course, would like a better approach of testing them, right? And a one-factor ANOVA is a good solution to that because we can test the equality of all the means at once or simultaneously. Okay, so let's look at a particular example that we will illustrate throughout this entire discussion. And let's see if we can answer the question, is there a significant difference? Is there a significant difference between different age groups in terms of how much they sleep? All right, so that's the question that we're going to be exploring here. So the variable x that we're going to be looking at, actually let's call it y. So the variable y is going to be equal to the amount of sleep that people get, and then x is going to be, for example, age groups. Right? So these age groups are going to be partitioned in the following way, and of course this is not unique. You can choose different age groups if you want to. So category 1, this is going to be equal to the preschool and infant category, i.e. ages 0 to 5 years old. Category 2, this is going to be defined as the child category, i.e. 6 to 12. Category 3, let's define this as the teenager category, which is going to range from 13 to 18. C4 is going to be our adult or young adult category. Let's define that as 19 to 55. And then C5, let's define that as the elder group, which is going to be defined as 15 and older. Okay, so notice that in this case we have K is equal to 5 different groups for which we're going to sample. Okay, and in terms of the amount of categories, because technically this age group is a categorical variable, notice we're only going to be analyzing one of them. This is what makes this ANOVA method a one-factor or a one-way ANOVA. So a one-way or a one-factor ANOVA only considers one categorical variable. So if you want to analyze, say, 2 or more categorical variables like age group, gender, height, or some other types of categorical variables that you may want to consider, that would be what we call a two-way or a two-factor or a multi-way or a multi-factor analysis of variance. All right, so now that we have each of these categories defined for our categorical variable x, now we're going to collect the y values associated to each of these categories, ideally as much as possible. So now we're going to go out and gather our sample. And let's assume that our sample has the following structure. So our sample from category 1, let's assume is going to be 9.2, 8.7, 9.5, 10.2, 8.4. Category 2, let's assume we were able to sample 8.8, 9.1, 8.7, and 9.2. Category 3, let's assume we were able to sample 9.1, 8.2, 8.1, and 8.5. C4, let's sample a bunch of values in this category. Let's say 8.5, 8.7, 6.2, 8.5, 10.1, 8.2, 7.1, 8.2, 8.5, and 9.1. And our last elder category, C5, that's going to be equal to, let's assume, 8.9, 9.5, 9.2, 8.6, let's go 9.7, and 9.5. Right. So the reason I'm giving these examples in this long and detailed way is because I want to point out something. Notice that my samples in each of these categories are not necessarily equal to each other, and that's okay. Because notice in this first sample, so the number of values in sample 1, notice that we have 5 respondents. The number of values in category 2, we have 4 respondents. The number of values in category 3, we have 4 respondents. The number of values in category 4, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 values in that category. And notice that the number of values in sample 5 was equal to 6. So across each of these categories, that means that M would of course be the sum of our NKs, which is going to come out to 29 different respondents across all the different categories. And each of these cells or categories are of course of different value in terms of how many we sampled. So let us revisit the null hypothesis that we're actually testing here. So remember, the null hypothesis that we're trying to test is that mu1 equals mu2 equals mu3 equals mu4 and mu5, where 5 corresponds to the number of category subsets that we're actually interested in. So if we want to get a point estimate for each of these parameters mu1 down through mu5, then of course we know the sample mean is an unbiased estimator for the population mean. So we can find that x bar 1 is going to be equal to 9.2, x bar 2 is going to be equal to 8.95, x bar 3 going to come out to 8.475, x bar 4 is going to come out to 8.31, and lastly, x bar for our elder category is going to be equal to 9.07. So do we have sufficient evidence to believe, based on these point estimates, that the average amount of sleep pretty much is homogeneous across each of the categories or not? So that's pretty much the question that we're trying to answer here. Okay, so let's just also state a couple assumptions that need to be met in order for us to conduct this test. Of course, you should already know this from, for example, the pair difference of the pooled variance t-test and something like that, but let's just review. So assumptions, the distribution of sleep across each of those particular categories, this must be associated to a normal distribution, and the variance associated to each of these categories should be equal to some variance, say sigma squared, i.e. sigma 1 squared equals sigma 2 squared equals sigma 3 squared equals all the way down to the last category, sigma k squared. All right, that is the homosedasticity term, must be satisfied. Now, I'm not going to go into detail how to test the equality of several means, but keep in mind, at this particular stage, you should at least be able to conduct a pairwise comparison test. It does have its downsides, but we will eventually present a more better way, sort of like the one-way analysis of variance, but for variances, not means. All right, so those are some of the basic setups for the ANOVA table. Now let us look into how we're actually going to code this for the multiple linear regression approach. So how do we go ahead and code this problem into a regression model and build an equivalent null hypothesis for the equality of these means from the regression perspective? So there are of course different ways to code this problem into a regression model, but we will be using something that should be already familiar to you, and that is the reference cell coding approach. So we're going to be using reference cell coding, right? So that is, we're going to be using dummy variables. So we're going to have dummy variables, say xk, and this is going to be equal to 1 for classes ck, where k ranges from 1 to all the way down to, say, r minus 1. Let's assume we have r categories for our categorical variable. I guess you could say it's a subcategory. And 0 for otherwise, or cr for k is equal to r minus 1. All right, so that's the formal statement of it, but let's actually look at it for our particular example, just in case you don't know how to sort of understand that, right? So dummy variable 1, this is going to be equal to 1 for age group 0 to 5 and 0 otherwise. Then we're going to have dummy variable x2. This is going to be equal to 1 for age 6 through 12, 0 otherwise. Then dummy variable 3 is going to be equal to 1 for age 13 through 18, 0 otherwise. And then x4, this is going to be our last dummy variable. So notice that we have r is equal to 5 subcategories. That means we're going to only need r minus 1 dummy variables to represent that, where the first value is going to be 1. This is going to be for our age 19 through 55, and 0 is going to correspond to our age 56 plus. All right, so this is our reference group. And keep in mind, it doesn't matter which group you use as a reference group. Of course, your model will be different, but the conclusions will be the same. Okay? So once you have these dummy variables, then that means we have our multiple linear regression model. That means we have the model y is equal to what? Y will be equal to, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. Again, we don't need a beta 5 x5 because we only need 5 minus 1 dummy variables, and then we have our residual term epsilon. All right, so those are our dummy variable codings for our particular problem. All right, now let us see if we can sort of build this into our equality of means problem. So the first thing that we're going to do is we're going to define mu to be equal to mu1 plus mu2 all the way down to mu k, all divided by k. Right? So in our particular example, that means mu is going to be equal to mu1 plus mu2 all the way out to mu5 all over 5. So if the null hypothesis mu1 equals mu2 equals all the way down to mu k is true, then what will mu be equal to? Well, mu is just going to be equal to, let's say, well, if they're all equal to each other, that means mu1 is equal to mu k, mu2 is equal to mu k, all the way down to, say, mu k, all divided by k, and that means we're going to have k mu k's on top and k on the bottom, and that's just going to be equal to mu k. That is mu is equal to mu k. That is the average of all of the means is equal to the average of a particular population. Now notice I'm focusing on mu k because that is going to be our, again, reference group, okay? But of course you could say that mu is equal to mu2 or mu1 or mu5. It doesn't really matter here, but we're using mu k as a reference group, let's say. But again, it doesn't really matter. Okay, so let's see if we can sort of figure out what an equivalent null hypothesis is. So we want the null hypothesis that mu1 is equal to mu2 is equal to all the way down to mu k. We want this to be equivalent to a null hypothesis in the multiple linear regression realm that we're actually familiar with solving. In particular, beta 1 is equal to beta 2 is equal to all the way down to beta k minus 1 are all equal to 0. Now let's see if we can figure out what these beta 1, beta 2 down to beta k minus 1s are actually equal to each other. So let's just make a couple observations. So if mu1 is equal to mu k, that means mu1 minus mu k is equal to 0. If mu2 is equal to mu k, that means mu2 minus mu k is equal to 0. And we can repeat this process all the way down to if mu k minus 1 is equal to mu k, that means mu k minus 1 minus mu k is also equal to 0 here. Right? Now notice I have a bunch of parameters. Take a guess at what I'm going to define my betas to be. So this is going to be equal to beta 1, that's going to be equal to beta 2, and that's going to be equal to beta k minus 1. All right? And take a guess at what my beta 0, my intercept, is going to be. You can take a couple moments and maybe think about that. But we have this coding scheme that beta j is going to be equal to mu j minus mu k, where j ranges from 1 to all the way down to k minus 1, and beta 0 is actually just going to be equal to mu k. Right, and keep in mind that mu k, by definition, will be our reference group. So if all of your coefficients are equal to 0, all of your information for your reference group is going to be coded inside of the intercept of your multiple linear regression model. Right? So let's just take another look at our multiple linear regression model, but from the mean perspective, right? So remember, y was equal to beta 0 plus beta 1 x1, all the way down to, say, beta k minus 1 x k minus 1 plus epsilon. So we see that this is equivalent to the model y is equal to mu k plus mu 1 minus mu k times x1 plus mu 2 minus mu k x2 all the way down to mu k minus 1 minus mu k times xk minus 1 plus our residual term. So that is our equivalent perspective of our multiple linear regression model, but from the mean perspective. So now that we have our model built, both in terms of the betas and our mu's, now we need to figure out what are some point estimates for our beta 0, beta 1 down to beta k minus 1. Now, it might not be obvious if you look at this from the beta perspective, but if you look at this from the mu perspective, we should be able to get unbiased estimates for mu k and the difference of mu j and mu k, because we should know unbiased estimates of those mu's. So, what are the reasonable point estimates for our beta k's, right? So, one can find for our intercept, beta hat 0 is going to be approximated by x bar k, and beta hat j, so that is the differences of the means, is going to be equal to xj bar, that is the sample mean of category j, minus the sample mean of category k, and this is going to be true for j is equal to 1, 2, all the way down to k minus 1. So these are going to be our point estimates for a multiple linear regression model. So let's make a little table to sort of organize our results, and let's do it for our particular example. So our parameter and then our estimate, right? So we're going to have beta hat 0, beta hat 1, beta hat 2, beta hat 3, and beta hat 4, right? So beta hat 0 is going to be what? So that's going to be the mean of category 5, our elder group, which we found to be equal to 9.07. Beta hat 1 is going to be approximated by x bar 1 minus the x bar of our elder group x5, and that's going to be found to be equal to 0.13, and then you can find the others. So our second group minus the average of elders is going to be negative 0.12, and then negative 0.59, and then negative 0.76. Now if you sort of want to get an idea of what these numbers represent, remember these are differences. If all of the means are different, then all of their differences should be equal to 0, right? That's what we're trying to show. Because of all of their differences, if all of them are equal to each other, their pairwise differences should be 0, and that means the parameters associated to the model, i.e. these coefficients, should also be equal to 0 simultaneously, right? So this one, of course, is the largest in terms of the magnitude from 0. That means we will possibly reject the null hypothesis, or the baby null hypothesis, that mu4 is equal to mu5. So if we reject that all of the means are equal to each other, the first mean that you should be investigating, or the pairwise means, probably should be mu4, right? Because that appears to be the most difference from our reference group, group 5. Right? So that is our point estimates for our parameter. Now what will be our actual model? So our model, or our predicted values, is going to be equal to 9.07 plus 0.13x1 minus 0.12x2 minus 0.59x3 minus 0.76x4. So those are our predicted values for our age group. So if I were to pick a particular age group, I should have a predicted value of the amount of sleep that that age group participant is going to have. So our predicted value for values 1 through 5, so that is our infant preschool age group, that's going to be equal to 9.07 plus 0.13. So since we're in the first age group, x1 is going to be equal to 1, and all of the others are going to be 0. So that's going to be true through 1 through 5. And then y hat 6 through 9, so the predicted values for the 6th through 9th participant, so that is going to be our children group, so that's going to be equal to 9.07. So since we're in the second group, the first one's going to be 0, the second coefficient is going to be, or the second variable value is going to be 1, so that's going to be equal to minus 0.12 times 1, and then plus 0 plus 0. And then y hat 10 through 13. So this is going to be our teenager group. That's going to be 9.07 plus 0 minus 0.59 times 1 plus 0. And then we're going to have y hat 14 through 23. That's going to be equal to 9.07 plus 0 plus 0 plus 0 minus 7.76 times 1. And what about our last values, 24 through 29? That's our elder group. That means all of the coefficients should be equal to 0 thereafter, right? So that's going to give us all of our predicted values, right? And then you can calculate what those are, of course, and then you can calculate, for example, residuals. So the first metric that we usually want to care about is going to be the error sum of squares, or the sum of squared residuals. And remember, that's going to be equal to the sum of y minus y hat, the quantity squared. So we're going to have our value minus the predicted values squared for all of the respondents. K is equal to 1 to m, right? And you should be able to find that's going to be equal to approximately 13.56. Okay, and if you want to look at this across each category, technically that's going to be the sum from I is equal to 1 to R, where R is the number of categories or subcategories, of the sum from J is equal to 1 to the sample size of each of those baby groups of Yij minus the average of group I. All right, so that's the more formal calculation of the SSE if you just look at the table of the groups. Once you have your SSE, then we should be able to calculate the MSE. Right? So what's the MSE going to be equal to? So the MSE is going to be equal to SSE divided by, usually it's m minus p minus 1 for the multiple linear regression case, but this is going to be equal to n minus k, where k corresponds to what? That's the number of means in our null hypothesis, so mu1 equals mu2 equals mu3 all the way down to mu5 in our particular category, right? So k is equal to 5. Now, if that is the case, remember, if we have 5 means, how many predictors do we have in our model? So if we have k means, that means the number of predictors in our model is going to be equal to k minus 1. So if p is equal to k minus 1, that means k is equal to p plus 1. That means that's going to be equal to what? SSE divided by n minus p plus 1, which is going to be equal to this error sum of squares divided by m minus p minus 1. And notice that that is the same exact formula as we had for a multiple linear regression model, so nothing new is being introduced here. So using this formula, SSE divided by n minus k, or n minus 5 for a particular sample, one can find that the MSE is going to be approximately equal to 0.565. So we have these two very important metrics which are associated to our ANOVA table for multilinear regression, which is great. Now, in terms of interpretation of the SSE, a very useful interpretation of the SSE sort of describes the variability within these subgroups, right? So we're not really comparing to all of the subgroups compared to one another. We're just talking about the variability within each of those subgroups, okay? So if the variability within each of these subgroups are, very small, then the SSE should be closer and closer to 0. Right? Now what I want to do is calculate the SSM. Now, up to this point, I've usually just calculated the SST, and then from SST, I calculate the SSM. But I'm actually going to introduce a way that we can actually calculate the SSM directly, and then we're going to see if it's equal to the SSE like we typically would calculate. So I'm going to denote y bar j. This is going to be equal to the mean of y group j, right? So that's going to be the average of, for example, the sleeps of the infants, the sleeps of the children, the sleeps of the elders, and so on. So it's the average of each of those groups. And then we're going to have y bar bar. So this is going to be the mean of all y values. Some people also refer to this as the grand mean. So it's the mean of all of the, 29 different respondents that we had for our particular sample. So the SSM, the model sum of squares, this is going to be equal to the sum from j is equal to 1 to r, where r is the number of subgroups, of nj times y bar j minus the grand mean squared. Right? And if you use all those informations, you should find that that's approximately equal to 4.002, a very important metric. And then from this, we can calculate the MSM. So the MSM is going to be equal to the SSM divided by k minus 1. And remember, if k is equal to p, k is equal to what? What's the relationship to that with p? So remember that p was equal to k minus 1, so that means k is equal to p plus 1. So if you want to sort of compare that to the old MSM formula, that's going to be equal to SSM divided by p plus 1 minus 1, which is the same as SSM divided by p, the number of predictors in our model. So that, of course, still satisfies the same relationship with our old MSM formula from before. So once you have that, then we're going to have that MSM for our particular example is going to be equal to that SSM, that 4.002 approximate value, SSM, divided by k minus 1. Remember, k is the number of means that we're going to be dividing by 4 here, so that's going to be approximately equal to 1.001. Okay, and in terms of interpretations for the SSM and MSM, this talks about the variability between, some people also say across the groups. Okay, and that's how you calculate the SSM and the MSM for a particular model. So that's pretty exciting. So what about the SST and the MST? How would we calculate them? So if we use the relationship that we have proven before, that SST is equal to SSM plus the SSE, or the total sum of squares is equal to the model sum of squares plus the error sum of squares. That means if we add those two values up, we should get 17.56. Now, what is going to be equal to the MST? So the MST is going to be equal to the SST divided by the degrees of freedom. So what is the degrees of freedom for the MST in this little test that we're working with here? So let's build a little table. So here's our degrees of freedom. We have our model, we have our error term, and then we have the total. Remember, they should add up. So for the model degrees of freedom, we had k minus 1. For the error term, we had n minus k. And if we do k minus 1 plus n minus k, we're just going to be left with n minus 1. So it's the same exact degrees of freedom as we had before. So that's SST divided by n minus 1. So if you calculate that, that's going to be approximately equal to 0.6272. Now question, is this equal to the variance of the y values? So is the MST equal to the variance of all of our y values? Yes. Right? So you still can use the same exact shortcut as before, find the variance of y, calculate the SSE, and from it you can calculate the SSM just as before. Now isn't that great, right? Now just a quick couple of interpretations before we move on to the conclusion of this. If the SSM is significantly greater than the SSE, what does that imply? So that means the variability is due to differences between the groups. Between the groups, not within the groups. Right? Because our variation is split into two pieces, within each of the groups and across each of the groups, right? And if the variability is due to difference between the groups, what does that mean? That means we do have evidence to believe that the means, mu1, mu2, all the way down to say mu k, where k is equal to 5 for our particular example, are substantially different. All right, so is there a test statistic for this? And you probably can guess what that is. So the f-test statistic is going to be equal to SSM divided by SSE multiplied by n minus k divided by k minus 1. Now, does this formula look familiar? Well, it should, sort of in disguise. That's the same as the SSM divided by k minus 1, all divided by the SSE divided by m minus k. And that, by definition, is of course going to be equal to the MSM all over the MSE, and that's going to be associated to the F distribution with k minus 1 degrees of freedom and n minus k degrees of freedom on the bottom. And remember, through our analysis, this is equivalent to an f-test statistic that is equivalent to f. Remember, k minus 1 was the same as p, and n minus k was the same as m minus p minus 1. So it's the same f distribution as we had for our multiple linear regression model from before. So that's a very, very nice conclusion. So if we continue with our example and calculate the f-test statistics that we have, because we already have our MSM and our MSE, then we're going to have a test statistic to be equal to, remember, MSM all over MSE, the mean quotient, and that's going to be approximately equal to 1.7709. And remember that this is going to be associated to an F 5 minus 1, 29 minus 5 distribution, which is just the same as a F 424 distribution, and one can find that this f-test statistic associated to that particular distribution is going to create a one-sided p-value of approximately equal to 1676. Right? So if you're using a 5%, then that p-value would be greater. So if you are working with an alpha value that is less than 0.16, let's say, that means our p-value is not low to reject. That means we're going to be failing to reject the null hypothesis that beta 1 is equal to beta 2 is equal to, all the way down to beta k minus 1, which is beta 4, is equal to 0. Right? And remember, this is equivalent to failing to reject the null hypothesis that mu1 is equal to mu2 is equal to all the way down to mu5. Right? That means if we're failing to reject the null hypothesis that those are equal, that means what? That means we have evidence to believe that sleep amounts are homogeneous, or average sleep amounts are homogeneous across age groups. And that is how you conduct a one-way ANOVA for the equality of means via multiple regression. So I hope you enjoyed. We're going to be taking a look at how to do the equality of means ANOVA test without regression, and we're also going to be taking a look on how to do it if we have two categorical variables or possibly more than two categorical variables, both from the multiple regression and the non-multiple regression approaches. So I hope to see you there. Take care.